Hi class, welcome to Unit 4, Lesson 7, where today we'll look at polarization of light. So today's learning goal, students will be able to demonstrate understanding of polarization of light and ways of achieving polarization. I know that I've achieved these goals if I can describe in detail polarization of light and the ways of achieving polarization and its applications. Investigate if transverse and longitudinal waves can be polarized or not. Solve problems related to polarization, and apply learning and this thinking to daily life problems. So what is polarization? It's the act of confining the vibrations of a wave to one direction. Light waves, for example, travel in all directions, and if such a wave passed through a filter that allowed the vibrations to occur only in one plane, then the wave would be plane polarized. So a plane polarized wave is a wave that can vibrate in only one plane, and an unpolarized wave is a wave that vibrates in all directions perpendicular to the direction of travel. A polarizer is something that can be either natural, like clouds, or artificial, like filters and experiments, in a way to achieve polarization. So there's two types. So transverse waves are always linearly polarized with its vibrations always along one direction, just by nature of transverse waves. As you can see in the diagram here, we have direction of vibrations is up and down, and if our filter is up and down, then it can pass appropriately with a wave direction this way. And however, if you were to change and make the slit or filter in opposite direction, or a different direction from its linearly polarized one, it wouldn't be able to pass. And so the wave can't pass here through this filter. So when we look at light, when light passes through a polarizing filter, the light waves are polarized in one plane, just like we said. If the filter is oriented in such a way that the vibrations are horizontal, then we call the light horizontally polarized, which happens here. Polarizes it and becomes, notice the filter is horizontal and produces, when we have unpolarized light in all directions, comes in here, and it only allows through the horizontal direction of light, waves of light. And so if the horizontally polarized light falls on a second polarizing filter, the analyzer, which is responsible for polarizing in the vertical plane, the light energy is almost completely absorbed. As you notice, near zero intensity, barely any of it comes through because you have perpendicular filter versus the waves allowed. And then when the axes of the two filters are parallel, so if we had two horizontals here or two vertical polarizing axes, then the polarized light from this first filter, say it stayed horizontal, and we had a second one that became horizontal instead of this vertical, it would pass the second filter without any further absorption. So it would just freely come by and stay with horizontal arrays. So we have polarized lenses that you've heard of in cameras. And so a polarizing material or Polaroid lens will only allow the polarization parallel to its axis to pass through, similar to what we saw before, and thus it reduces the light intensity, only allowing a certain amount of the original through. So two Polaroids can be used to control the light intensity, which is why Polaroid lenses are very useful in eliminating glare and unwanted intensity, bursts of intensity in photos. And so similar to before, we have unpolarized light with an intensity of S. If we have a transmission axis in our polarizing material, if it's only allowing vertical, for this particular filter, vertical waves with this orientation, then we get a polarized light intensity after the fact, and the rest of it is absorbed, and the polarized light intensity is half of the original. And so we can eliminate glare in our photos, like with using this concept. So absorption doesn't just occur because it's vertical and horizontal orientations, but it's because they are perpendicular and to right angles of each other. So any polarizing filters with axes that are right angles to each other, you'll get the same effect. So if you notice here in B, you have polarizing filters with axes parallel, so we have some partial transmission of light. And then if we turn the same filters, either two copies, and if we turn them perpendicular to each other, then we get polarizing filters with perpendicular axes have no transmission of light. This really dark spot because of not because they're vertical or horizontal. Notice these represent the horizontal lines, so we're on a angle here, but it's the axes, so it doesn't matter. It's just the right angle nature and not vertical and horizontal orientations. So what about the other type of wave we looked at? Longitudinal waves, can they be polarized? If light traveled as a longitudinal wave, the vibrations could only be in one direction and the direction in which the wave was traveling. Such a wave would pass through a pair of polarizing filters without being polarized. So in other words, longitudinal waves, they can't be polarized because of the way they act. However, light, which we have already decided behaves like a wave, must then behave like a transverse wave, not as a longitudinal wave. So notice here with our longitudinal wave, we have the horizontal filters. It passes unaffected, just like our transverse waves. However, when we have our Polaroid setup, one vertical, one horizontal, or perpendicular to each other, doesn't matter about the orientation, longitudinal waves pass through unaffected, and so they can pass through polarizing filters no problem. But we say that light must be a transverse wave, and because it's subject to polarizing effects. So we can achieve polarization using 4 different ways. We have double refraction, reflection, scattering, and polarizing filter or Polaroid. So the first, double refraction, the property of certain crystals like calcite being able to split an incident beam of light into 2 beams. When a beam of unpolarized light strikes the calcite, it is separated by the crystal structure into 2 beams polarized at right angles. So we have the incident beam coming in. Notice the unpolarized light with all the directions, and it it refracts into 2 beams, and it's naturally just essentially polarizes or filters them, making one making them both at a right angle. Polarized at right angles or perpendicular, right? And so it just does this naturally. So another way is reflection, when some absorption takes place at the point at which the light is reflected off a smooth surface. These light waves are reflected from a flat surface are partially polarized in the horizontal plane. So they come in incidentally on the unpolarized way of all directions, reflect, and become partially polarized in the horizontal plane. And so light reflected by a non-metallic surface is polarized in the horizontal plane partially. And in the real world, a lot of glare comes from horizontal surfaces like this, such as a body of water or the hood of a car or paved road. And so if this glare is partially polarized in the horizontal direction, how do we counteract it? Well, we take a Polaroid filter and make it vertically oriented in the vertical plane. And it's in order to absorb most of the polarized light in the horizontal direction. And so that's the case with Polaroid sunglasses, that they can absorb all this horizontally polarized light reflected from these horizontal surfaces, and we don't have as much glare from these surfaces like bodies of water reflecting and such. So scattering is also a process involving polarization. It's the changing the direction of particles or waves as a result of collisions with particles. So light from the sun passes through our atmosphere and encounters small particles that scatter the light. Scattering causes the sky to appear blue because the shorter wavelengths, like violet and blue, are scattered more than the longer wavelengths, shades of orange and red. So this scattering also causes the light to be polarized. You can demonstrate this polarization by looking at the sky through a rotating Polaroid sheet, like this, or through polarized sunglasses. And the amount of polarization depends on the direction in which you look, being greatest at right angles to the direction of the light from the sun. So if you notice here, the direction of the sunlight is coming this way, scattered by the atmospheric molecule. And in the direction of the sunlight, unpolarized, it's no change. And then we have partially polarized when we're at a slight angle from the direction of the sunlight. And when we're at a right angle here, we get polarized light. And at right angles, it's the greatest amount of polarization. And the last we've seen a little bit already is the polarizing filters or Polaroid in devices and other things we make. And it's using a polarizing filter, which is called a Polaroid, and it's just a plastic or light polarizing material. Because Polaroid made it easy to produce polarized light, many everyday applications became feasible. Sheets of the new plastic could be used as convenient analyzers, making it easy to detect polarized light in nature and determine its plane of polarization. So the idea of polarizing waves and specifically polarizing light is very useful in everyday life. So we've already covered that polarizing sunglasses are used to reduce the glare of reflected lights by using vertical filters to try and filter out mostly horizontally polarized glare, just like from a body of water here, for example. Very useful. And the LCD screens on a laptop computer uses polarized light to make pictures by having a polarizer that helps polarize and filter out this backlight from the back of the computer if you're viewing from this way, and it helps control how to display this on the front for you to view it comfortably and accurately. And Polaroid filters are also used heavily in photography. Photographers use these filters to enhance photographs of the sky and clouds that are subject to a lot of glare and interference. Since large stretches of the sky are significantly polarized, the polarizing filter makes the clouds more prominent by reducing the glare. And so when you see the cloud effects are enhanced when we add this, when we have the original here, and we use a polarizing filter, we're able to fight some of those four polarizing effects that we were talking about and make these clouds much more clear. And the last very useful and popular application is in 3D movies. Polarization has been used to produce the illusion of 3 dimensions at the movies. It does this by overlapping 2 pictures shot by cinema cameras a few centimeters apart in the matter of how human eyes would work. And then they're projected onto the screen with a pair of projectors, and we each are equipped with a Polaroid filter. And so the idea is to have the directions of the polarizations in those filters to be mutually perpendicular. And so the idea is to have when you wear the glasses, that you have they are especially have filters matching the ones of the projector, and they are supposed to use filters to match the left and right lenses, and using that idea of the perpendicular filter versus the to use these perpendicular filters to match so that your left eye is viewing only images from the left camera and the right eye is only viewing images from the right camera. And then when the brain receives different left and right eye inputs, the screen looks like a window into a three-dimensional panorama or window. And so this all comes from, all these useful applications are coming from this behavior of waves and polarization. And so that's the end for today.